Today we're going to look at a few specific kinds of examples of ways we can apply sequences in series to real-life examples. Let's take a look at example 1. David has the flu, so he gets antibiotics. He's told to take 500 milligrams every 12 hours for 8 days. Knowing that the presence of a prescription drug decays exponentially in the body, he knows the amount of drugs in his body will build up as he continues to take more and more. In fact, he found out that after 12 hours, 8% of the drug is still in his body. So immediately after he takes the first antibiotic, he's got 500 milligrams in his body. But just before he takes the second dose, he's taking the dose every 12 hours. And we know that 8% is still left in the body after 12 hours. So immediately before he takes the next dose, he's going to have 8% of 500 milligrams remaining, which is 40 milligrams. And then immediately following his second dose, he's got the 40 milligrams left from the first dose, plus an additional new fresh dose, which means that he's got 540 milligrams of drug in his body. This is what he means by the buildup, is that he still has some of the original drug dose left, and then he's taking more, so he now has more in his body than he did after the first dose alone. Okay, so just before the third dose, for example, now he's got 8% of the 540 milligrams. That was what was in his body right after his second dose. So just before his third dose, another 12 hours has passed. He's got 8% of the 540 left, plus, before the dose. So this would be 43.2 milligrams. Well, that makes sense. He's got more built up because he has remnants from the first dose and remnants from the second dose. So if Q sub n is the amount of drug left in his body after the nth dose, evaluate all of these guys. So Q sub 3, we know he has 43.2 milligrams left over from the first and second doses, plus a fresh dose, puts him at 543.2 milligrams. And Q sub 4, now he's going to have 8% of the 543.2 milligrams left over. That's how much he had after the third dose, plus, again, a fresh dose, is going to put him at 543.464 milligrams. And Q sub 5, again, we've got 8% of the last dose left over, plus a fresh dose, puts him at 543.47712 milligrams, and so on. Double check my math. Again, 8% left plus a fresh dose. So let's make sense of what's happening. A single dose is going to decay exponentially in the body, right? You start with 500 milligrams. Eventually, you've got nothing left. That's why we have this horizontal asymptote at y equals 0. Eventually, it's all going to decay, and it decays exponentially. But what's happening in his body for the total concentration of drug is a little bit different. He starts at 500, that dose decays, and then 12 hours later, he's going to see a spike up to 540 milligrams because he just took a new dose, plus he's got a little bit left over. Then that amount's going to decay, and after 24 hours, again, he's going to spike up a little bit more, and that's going to decay, and so on and so forth. So on this interval, from 0 to 192, at what point was the concentration of drug the lowest? The concentration of drug would be lowest here at this point, because he's decayed almost everything from the first dose, and he has not taken any additional doses. So at 12 hours, the concentration is lowest because he's got the most decay, plus nothing else added on. But at what point will it be the highest? It'll be, look at this trend line. The spikes sort of continue up and up. I'm making it more dramatic than it really is. But the amount of drug in his body will be highest immediately following his last dose, because he'll have the greatest amount of buildup from all the other doses, plus that last dose will not yet have decayed. Okay, let's look at one more example in this video. Because of friction and air resistance, each swing on a pendulum is a little shorter than the last one. The swings form a geometric sequence. Suppose the first swing has a length of 100 centimeters, the return swing is 98 centimeters. Draw a picture. So what's happening is you have some object that's swinging, and the first swing was 100 centimeters long. And then when that object swings back, this perhaps would be more obvious, more accurate. It's going to swing, and then when it returns, it's not going quite as far. It's only going 98 centimeters. And then we would anticipate, again, it's not going quite as far, it's not going quite as far. Eventually, this guy's going to slow down and be still. So what's the distance traveled on its 10th swing? Well, don't be fooled into thinking the sequence would be 100 centimeters, 98 centimeters, 96 centimeters, and so on, because it's telling us this is a geometric sequence, which means there must be, instead of having a common difference of subtracting 2, there must be a common ratio. Well, what do you multiply 100 by to get 98? I have no idea. Go backwards by dividing 98 by 100. That'll give you 0.98. So the common ratio must be 0.98, which makes the third swing not 96, but some other number. So our sequence is going to look like this. F of n is 100 times, since it's a geometric sequence, it should look like an exponential relationship. The 10th swing would be 9 swings after the initial. So we're looking for f of 9 is 100 times 0.98 to the 9th power, which is 83.4 centimeters. So yep, this pendulum is slowing down sort of slowly. What's the total distance traveled during the first 10 swings? That would mean how far did it travel the first swing and the second and the third and the fourth. You can tell that we're adding terms up. So we're adding up terms from this sequence, 100 times 0.98 to the nth power, where we're starting with the initial term and going until 9 terms after the initial term, so 10 total swings. And you get that this sum is 914.6 centimeters. Well, that makes sense, because if each swing were 100 centimeters long and you've taken 10, that would be 1,000. But we know that the swings are getting a little bit shorter each time, so we end up traveling a total distance of just slightly under 1,000 centimeters. Final question of the day is, how are B and C different? This total distance is asking us to add up individual distances. That's why we're using a series. Whereas this is an individual distance traveled. That's why we're using just a term from the sequence.